I wanted to describe a more interesting application of the pigeonhole principle and show you how you can use it to solve some perhaps tricky counting type problems. So we'll call this application of pigeonhole principle. Let S be a set of 10 distinct positive natural numbers between 1 and 100. Then the claim is that there must exist two different subsets, two different non-empty subsets that sum to the same value. Okay, so you take any set of 10 distinct positive natural numbers between 1 and 100, and there must exist two different non-empty subsets that sum to the same value. How are we going to apply the pigeonhole principle? Well, the pigeonhole principle is about placing pigeons into holes. So we're going to how many different sums are there? So the smallest possible sum is if the number 1 appeared in S and you took the subset of just the number 1 and added it up, then the smallest possible sum that you could possibly get is 1. It's non-empty. And the largest possible sum the largest number that could be in the set is 100, and we know that the set has 10 distinct positive numbers, so the largest possible sum is certainly less than 100 times 10, which equals 1,000. Okay, so here are all the possible sums that could occur. When you take a subset, 1, 2, 3, 4, and so on and so forth, all up through 1,000. Now you could imagine, what we're trying to prove here is that there are two different subsets that sum to the same value. So every time we have a subset, so let's say that we choose T that is some subset of S, then we can assign T, we can consider the sum of all of the elements of T, and that will, T will have some sum that will correspond to some positive integer in this list. And we could choose another subset, T prime, and that's going to have some other sum on this list. And what we're trying to prove is that there exists some subset U not equal to T such that U and T both map to the same sum. So how many different subsets are there of S? Well, S has 10 distinct positive natural numbers in it, so the number of subsets is 2 raised to the power 10, and we're only considering non-empty subsets. That's 2 raised to the power 10 minus 1. This equals 1,023. But notice that 1,023 is greater than 1,000. So we have 1,023 different subsets. Each one will get assigned to one of these values corresponding to its sum. And by the pigeonhole principle, since there are 1,023 subsets, and that's larger than 1,000, there must be two distinct subsets that map to the same sum. That proves the claim. I wanted to give you another example of using the pigeonhole principle to solve a non-trivial problem in math. This problem deals with subsequences of sequences What is a sequence? It's simply a list of numbers. So for example, 2, 3, 1, 7, 10, 4, 0. It does not need to be in sorted order. Okay, so this is a sequence of numbers. What is a subsequence of this sequence? Well, it's another sequence of numbers that's obtained from this sequence by removing some elements. So for example, and preserving the order. So if I remove 3, 7, and 10, I'm left with the subsequence 2, 1, 4, 0. Okay, so they're both sequences. This is a subsequence of our original sequence. Okay, and the problem that we're going to solve is as follows. So given a sequence of n squared plus 1 distinct numbers, so we're given a sequence of n squared plus 1 distinct numbers, and we want to prove that there exists a subsequence of length n plus 1, and here's the catch, that is strictly increasing or strictly decreasing. Okay, so given n squared plus 1 distinct numbers, prove there exists a subsequence of length n plus 1 that is strictly increasing or strictly decreasing. Let me do a brief example. So if we're given the sequence 8, 11, 9, 1, 4, 6, 12, 5, 7, 2, then how many numbers do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the length of the sequence is 10. So 10 equals 3 squared plus 1. And then according to this problem, there should exist a subsequence of length n plus 1, which in this case is 4, that is strictly increasing or decreasing. Okay, and let's see, can we find one? Okay, 9, 6, 5, 2. That is a subsequence that is strictly decreasing. So there we found one. There are probably others. So now I'm going to prove to you that this problem is correct, but I suggest you first give it a try yourself. It does involve an application of the pigeonhole principle. Okay, let's solve the problem. So we have a sequence of numbers A1, A2, A3, and so on and so forth, all the way through n squared plus 1. These are our distinct numbers. They may not be sorted. And now with each number, I'm going to associate a tuple. Okay. So this tuple, so A2 is going to get assigned a number I2 and D2. Okay. And this I2 is going to be the length of the longest strictly increasing subsequence starting at A2, and D2 will be the length of the longest strictly decreasing subsequence starting at A2, and using A2. So more generally, we'll say, so we'll define the tuple ik, comma dk to be the lengths of the longest increasing and respectively decreasing subsequence that starts with a k. Okay, so we'll have I1 D1, then we'll have I2 D2, and so on and so forth. I n squared plus 1, d n squared plus 1. Now it's pretty easy to see that the length of the longest increasing subsequence that starts with the last element is 1. I mean, if you start with the last element, there are no elements after you, so you have to be 1. And the length, similarly, the length of the longest decreasing subsequence that starts strictly decreasing subsequence, so these should be strictly increasing and strictly decreasing. The length of the longest strictly decreasing sequence starting with an squared plus 1 is also 1, because there's only one number left. We could do a slightly more interesting example. I guess 2, 4, 3, 5. The length of the longest increasing subsequence starting from 2 is 3, because you have 2, 4, 5. You could also use 2, 3, 5. The length of the longest decreasing subsequence starting at 2 is 1. So everything is larger than 2. So 2 would get assigned 3, 1. 4 would get assigned, well, there's a subsequence of length 2 starting at 4. And there's a subsequence of length 2 starting with 4, also 4, 3. So that's 2, 2. 3 would get assigned 2, 1. And 5 gets assigned 1 and 1. Okay, so I think we're ready to solve the problem. So we're going to do a proof by contradiction. Assume that the lengths of the longest increasing and decreasing subsequences are both less than or equal to n. So remember, we're trying to prove that there exists a subsequence that's strictly increasing or decreasing of length at least n plus 1. So I'm going to, by way of contradiction, assume that the lengths of the longest increasing and decreasing subsequences are both at most are less than or equal to n. Okay, that means that the number of distinct tuples ik, dk. Well, how many distinct tuples are there? Well, since the length of the longest increasing sequence can be at most n, then this number can be between 1 and n. Similarly, this number can be between 1 and n. So there are at most n squared distinct tuples. That means when we look back at our original sequence, a1, a2, a3, a n squared plus 1, by the pigeonhole principle, two of these numbers, let's say a2 and let's say aj here for some j, so two of these numbers must have the same tuple. Okay, so a2, so that means, for example, that a2 d2 must equal I2d2 must equal ij dj. Remember that every number gets a tuple, and since they're at most n squared tuples, then and they're n squared plus 1 numbers, 2 of these elements here must get the same tuple. Okay. But this is going to lead immediately to a contradiction. So, for example, case 1 is that A2 is actually less than AJ. Okay, so if A2 is less than AJ, then consider the longest increasing subsequence that starts with AJ. It's of length IJ. But now I can make it longer by starting it instead with A2. So I can take A2, and then append this longest increasing subsequence starting with AJ. That's going to, if A2 is less than AJ, then the sequence A2, AJ, and appending the longest increasing subsequence starting with AJ, this will correspond to a strictly increasing subsequence of length I2 plus 1. But we said that the length of the longest increasing subsequence starting from A2 was I2. But now we've constructed one that's even longer, I2 plus 1, by starting here and then taking this longest increasing subsequence. So that's a contradiction because the length of it should have been I2, not I2 plus 1. And our other case is that A2 is greater than AJ. Okay, now we're going to build an even longer strictly decreasing subsequence. We said that this tuple says that the longest strictly decreasing subsequence starting with A2 is D2, which is equal to DJ. But now I'm going to start with A2, and A2 is greater than AJ, so then I'll follow it up with AJ, and then I'll take the longest decreasing subsequence, strictly decreasing subsequence starting from AJ. That has length DJ, and now plus 1, because I've appended A2 onto the front of it. And again, this is a contradiction because we said that the length of the longest decreasing subsequence starting at A2 was D2, not D2 plus 1. I should say this equals D2 plus 1. DJ and D2 equal. D2 and DJ equal each other, I2 and IJ equal each other. So if there were two numbers in this sequence that had the same tuple associated with it, then we can build longer either increasing or decreasing subsequences starting from A2, contradicting the value that A2 had from its original tuple. And how did we find, or how did we state the existence of A2 and AJ, both of which had the same tuple? We applied the pigeonhole principle. There are at most n squared tuples and n squared plus 1 elements here in this sequence. So this is a slightly more subtle and interesting application of the pigeonhole principle. If it didn't make sense the first time, try watching it just one more time and you'll probably get it.